For decades, we've pictured the inside of a cell as this perfectly organized little factory. It's a world of tiny biological machines, right? Each with one specific job, all working tirelessly to keep us alive. But what if that whole picture is fundamentally incomplete? We've all seen them in our biology textbooks. These little workhorse proteins called enzymes, each one supposedly built for a single, highly specific purpose. They were the predictable, the reliable assembly line workers of the cellular world. Well, it turns out a lot of these enzymes are leading a double life. And this hidden reality? It's changing pretty much everything we thought we knew about health, about disease, and about the incredible complexity of life itself. So first, let's just rewind a little bit and go back to that classic textbook definition. What's the job we thought these enzymes were doing all day long? Okay, so think of an enzyme as a super specialized factory worker. Its entire existence, we thought, was dedicated to just one task on the cellular assembly line. This is what we call its canonical function. For example, a glycolytic enzyme's day job is to help break down sugar, or glucose, step by step to generate energy for the cell. Pretty simple, specialized, and absolutely essential. But here's where it gets interesting. As scientists started looking closer, they began to notice something strange. These dedicated little factory workers were like clocking out of their day job and picking up a second shift, doing something completely different. And we're not talking about some little hobby here. This second job, this secret life, has profound consequences for the cell, especially when things go wrong. This is what researchers call a non-canonical function, but honestly, the best way to think about it is as a side hustle. It's a second job, totally unrelated to metabolism, where the enzyme acts less like a factory worker and more like a manager, or a messenger, or in some cases even a saboteur. And this isn't some rare fluke. It is incredibly common. I mean, just look at this list of really well-known enzymes. Their day jobs are all related to glycolysis. That's the cell's main energy production line. But their side hustles, they're all over the map. PKM2 moonlights as a gene activator. FBP1 actually blocks cancer signals. And GAPDH, it can even trigger controlled cell death, a process called apoptosis. This dual role system is happening everywhere inside us, right now. And this is where the story takes a bit of a dark turn. Because these secret side hustles can be hijacked by one of our most formidable diseases, cancer. So let's meet our first double agent, an enzyme called PKM2. In a normal, healthy cell, it's a loyal worker in that glycolysis factory. But in a cancer cell, it gets corrupted, and it starts working for the enemy. So, how does this happen? Well, first, cancer signals basically flip a switch on PKM2, changing its shape. And that's the signal for it to abandon its post on the factory floor and travel to the cell's command center, the nucleus. Once it's there, instead of breaking down sugar, it acts as what's called a co-activator, turning on genes like HIF-1 alpha that tell the tumor to grow, build new blood vessels, and just thrive. It's not a worker anymore. It's a rogue manager fueling an insurrection. But not all of these side hustles are villainous. In this whole cellular drama, there are heroes too. There are enzymes whose secret lives are actually dedicated to fighting back against cancer. Okay, meet our undercover agent, FBP1. Its day job is in a process called gluconeogenesis, which is basically the reverse of glycolysis, but its side hustle makes it a really powerful tumor suppressor. It's so effective, in fact, that a lot of cancers will actively try to shut it down. FBP1's method is pretty much the mirror image of what PKM2 does. It also travels to the nucleus, but instead of activating HIF-1 alpha, it directly blocks it, cutting off a key growth signal for the tumor. But it doesn't stop there. It also intercepts a crucial message in another major cancer pathway, which effectively shuts down a whole chain of command that would otherwise drive the cancer's growth. It's like a double-barreled attack against the tumor. So here's the really crucial insight here. These two jobs, the metabolic day job and the regulatory side hustle, they're not random. They are deeply and intelligently connected. It's a system that allows the cell to adapt to its environment. You see, these enzymes aren't just mindless workers, they're sensors. They're constantly monitoring the metabolic state of the cell, how much fuel is available, how much energy is being used, and they actually change their job based on that information. Aldolase is a perfect example of this. When the cell has plenty of sugar, this molecule, called F16BP, is abundant. So aldolase is busy at its workstation, doing its day job in glycolysis, fueling cell growth. But when sugar levels drop, so does the amount of F16BP. This frees aldolase up. It leaves its post and moonlights as a regulator, helping to activate a master switch called AMPK. That's the cell's low-energy alarm. This tells the cell to stop growing and start conserving its resources. It's this beautiful, elegant system where the enzyme's job is dictated by the availability of the materials it works with.
Okay, this discovery of a whole secret layer of regulation inside ourselves is, of course, fascinating. But it also presents a huge new set of challenges and opportunities, especially when it comes to developing cancer therapies. I mean, think about it. If you design a drug that only blocks an enzyme's metabolic day job, you might completely miss its cancer-promoting side hustle. On top of that, whether an enzyme is helping or hurting can actually depend on the environment. A tumor that's starved for nutrients might use these enzymes very differently than one with a rich blood supply. This means we have to start thinking much more dynamically about how we target them. As the researchers who uncovered this world state so clearly, this isn't some tiny footnote. It's a fundamental shift in our understanding. We can no longer look at metabolism and cell signaling as two separate things. They are woven together by these moonlighting enzymes. It really makes you wonder, doesn't it? For nearly a century, we operated under this simple rulebook, but some of the most basic building blocks of life had a secret that we're only now beginning to understand. And it leaves us with a truly exciting question. What other fundamental secrets are still hiding, right there in plain sight?